Hello once again, this is Professor Doug. We are on Chapter 8 in Hibbler, Mechanics of Materials, and this chapter is about combined loading. So we're going to build on what we've previously learned, and we know that in practice, structural members are loaded in multiple methods, and that could be axial and with torsion, and also due to thermal stress. So we're going to see a couple of problems in this chapter and using Excel once again. So let's go right into that. The first one is a human bone, or it may be an animal bone, but it's a femur. And it has a load, axially loaded force of 75 pounds downward at an offset of 2 inches from the longitudinal axis of the bone. We want to know through the cross section AA what's the maximum normal stress. So it's going to be a combination of normal stress and bending stress together here. So axial stress and bending stress is going to give us our maximum normal stress on the cross section AA. And you're given the dimensions of the bone here. We're assuming it's a hollow tube. So that's an important assumption because it will inform our area and moment of inertia calculation. So let's get right to it. We're going to enter the load, the distance of the offset. So you can see by inspection it's going to create a clockwise moment, which will be negative, and that would be 150 inch-pounds, right? We have an inner diameter and an outer diameter. We're going to call those ID and OD respectively through the cross section. You can see it here in the cutaway. So let's go right to the equilibrium equations. The sum of the forces in the y direction for this bone in equilibrium, it's just in compression, so it's in equilibrium, and it should be 0. So up is positive, so you've got minus 75, and then you have your normal reactive force. So the normal reactive force is positive 75. You just bring that over to the other side of the equation. There you have that. The moments, assuming counterclockwise, is positive. It's going to be a negative 150 like we talked about before, 75 times 2, right? And that's just going to be moment minus 150 is 0, so the reactive moment is counterclockwise, which is positive. So there we go. We're in business now to go forward. We have area and inertia calculations, which are very straightforward. The area is just pi times OD squared minus ID squared, and the inertia is pi over 4 times OD to the fourth minus ID to the fourth. You can look these equations up in a structural manual or a manual of mechanics, and you will find those equations. And we're just doing the calculations here in Excel. So the combined stress on this is a combination of normal and bending. So normal we know is P over A or F over A. Here I'm calling it N over A. And bending, we've seen in a prior chapter is My over I, where Y is the outer diameter in this example. So for the bone in compression, you're going to have N over A, which is going to equal 75 pounds over the cross-sectional area, but it's negative due to compression, so it's minus 31.83 psi, and then you have your bending stress. So this was your axial stress, right, normal. This is your bending stress due to that 75-pound load applied at an offset of 2 inches. So the maximum moment, well, the only moment we know here is 150, so that goes into the equation. So My over I is going to be 150 times the OD, which is Y, outer diameter, divided by the area moment of inertia, which we got here in this purple cell. So that's going to give you minus 203.72. You just simply add them up. They're both negative, so the result will be negative also, minus 236 psi. All right, we're going to go to our next problem, which is, this is 811, an interesting problem using a combination of axial stress and thermal stress, right? So in this problem, you can see that we've got, I'm just going to try to close a few other windows here, if I could do that. My mouse is malfunctioning, maybe. So we're going to close 8.9, and we're not going to save that because it's already correct. And we're going to close our That's it. Okay, now, this problem, read carefully, a gas pipe. So it's transferring or conveying natural gas, let's say. Every 20 feet by concrete piers, it's supported and it lies on the ground. So there are rigid retainers at the piers. The pipe is fixed. Determine the longitudinal and hoop stress. So what they're asking you is sigma 2 is longitudinal and sigma 1 is hoop stress from this particular chapter. If the pipe, if the temperature rises 60 degrees Fahrenheit, we don't know the initial temperature, all we know is delta T. The gas within the pipe is pressurized, pressure is given, and the pipe has an ID and a thickness given, and the material is A36 steel. So we've got everything we need. Enter the length, convert it to inches by multiplying it by 12. Delta T was given. We don't know the original temperature, we don't need it. The pressure in the pipe, 600 psi, that's lowercase p. The ID, 20 inches. That means the radius is half of that, 10 inches. That's R. The thickness, lowercase t, was given, a quarter inch. So those are your givens. What you're going to look up is for A36 steel, the pipe material properties, the modulus of elasticity here, and the coefficient of thermal expansion, alpha. So it's a very small number, and those numbers are given here. Notice that I converted KSI to PSI. I want all of my units consistent here, right? So sigma 2 is longitudinal stress. Well, we don't know what it is right now. That's axial stress. So we're going to give it a non-zero starter value of 1. All right, we're just going to leave that as a placeholder. We know by load displacement equation and compatibility that the only actual lambda, which is thermal strain here, strain in the axial direction is going to be as a result of either pressure or temperature, and we've got these equations that are compatible, so we're going to set lambda f equal to lambda t. Well, lambda f is PL over AE. There's your old friend, the load displacement equation. P over A in this equation is just sigma. So that's the unknown, sigma 2. And then for the thermal strain equation, which we saw previously in chapter 4, it's just alpha delta TL. So we know all those numbers, so that's great. So let's do that calculation. Alpha delta TL is just this. It's alpha coefficient per degree Fahrenheit. Delta T is degrees Fahrenheit, so the units will cancel. L is 240, and so we're end up with inches for units, and we get a very small thermal expansion here, right? So then we have lambda f. Well, we said that P over A is sigma 2, so it's just sigma 2L over E. Well, we don't know sigma 2, so we're calling it 1. And if you look at the equation here, sigma 2L over E, everything else is known. So right now we get a number that doesn't really make sense because it's based on a sigma 2 of 1. You can see if we put in 0, which we don't want to do, you'd get 0, right? So we want a real number in there. We want the number to approximate or exactly equal lambda t. So we're going to do data what if goal-seek analysis here, and here's the information you need. So I just want to set, since this is already known, lambda t, and lambda f is unknown based on a variable sigma 2 that we are approximating right now as 1. We're going to go right to data. What if goal-seek, pop this window up, we want this flashing cell equal to the exact value of lambda t because they're required to be compatible, right? So we're going to say 9.5 e to the minus 2 by changing sigma 2 because that was a dummy variable, right? With dummy value. And there we go. So the answer is 11.5 KSI. We just rounded this to 11,500 and converted to KSI. And then what about sigma 1, hoop stress? Well, that's an easier calculation. It's just PR over T. P is the pressure in PSI, R is the radius in inches, T is the thickness of the pipe. So you just do that algebraically. It's 24,000 PSI, which is 24 KSI. And we've solved the problem here.